Hello everybody, this is Professor Iris Mayano coming to you with Day 13 lecture concerning logarithmic functions and also properties of logarithms. So one thing that we're definitely going to rely heavily on is our previous knowledge of exponential functions, because logarithmic functions are those functions' inverses. So definitely take that into account as we introduce this new type of function. It's basically just an exponential function reflected over the y equals x axis. If you want to think about it visually, switch the domains and the ranges in order to get an idea of what appropriate values as inputs and outputs are, and so on and so forth. We'll definitely get into all the details in this section concerning logarithmic functions, and then we'll also get into properties of logarithms, so just more things that you can do to manipulate logarithmic equations in the subsequent section 4.5. Okay, so we're going to introduce and label the basic logarithmic equation that you see here, y equals log base a of x. So what are all the different components here? Well, y is, and let me go ahead and get my drawer and play here, y is referred to as the exponent. Logarithms are equal to an exponent, basically. That's how we want to think of them in regard to connecting them to the exponential. The x here is called the argument of the logarithmic equation, and then a, this little bit here, is known as the base. You may be thinking, oh, is this the same as the base of the exponential expression involved in exponential functions? Yes, it is. The base is the base. And that gets me into the next thing that I want to introduce to you is the mantra that I use every time I'm going to convert a logarithmic equation into an exponential equation, because they have an exponential version to themselves, the logarithmic equations, that is. So if you want to convert a logarithm into an exponential, you can recognize that the base of the logarithm is the same as the base of the exponential version of it. The log is equal to the exponent, and the exponential is the argument. So when you're converting from a log to an exponential, the exponential itself is equal to whatever was inside of the argument position of the logarithm. So the argument is kind of like the input into the logarithmic function itself, okay? You put in an x, or whatever it's called. In this case, we're calling it x in this generic format. And you're going to take its logarithm base a. So that means it's going to, whatever's inside the logarithm, that's the result of your base being raised to the power that the logarithm is set equal to. So again, the base is the base, right? So let's actually color code these bits. So the base is the base. Let's start with that. That's your a. Base there is the base here in the exponential. That's the base is the base. The log is equal to the exponent. So the exponent is here and there. And then the exponential is the argument. Okay, so what color should we do the argument? Something distinct. Let's try this blue. So the argument there is equal to the exponential, is what we're saying here. And there you have it. So hopefully these three items, saying them over and over again as you go through the process of converting logarithmic equations into exponential equations, or the other direction, go exponential equation to logarithmic equation, this three-step mantra will work in order to get you from one to the other, okay? Now, because we know that logarithmic functions and exponential functions are inverses of each other, that's like how these things are being introduced, we know that in order to talk about the domain and the range of the logarithmic function, you simply must switch the domain and the range of the corresponding exponential function, the equivalent exponential function, that is. Okay? So, or sorry, not the equivalent, the inverse exponential function is what I meant to say. If you have a very basic logarithmic function that you're trying to graph here, what I recommend that you do is first graph its inverse, okay, which is can be reached by just putting these things in these particular positions, okay? So this is not converting from one to the other. We're not trying to make an equivalent exponential expression. We're trying to take the inverse, which if you are trying to calculate what the inverse is for a more complicated logarithmic function than just what I would call, this is what I would call the parent, then rely on the multi-step process that you went over in the beginning section of this chapter. The inverse, what was it, 4.2 one-to-one functions and their inverses, where you let your function name be called y and switch the x's and the y's and then solve. So converting from one to the other is going to be helpful in that process. Okay, oops, there we go. All right, so this is what this information right here is doing, is telling you what the inverse is. So what I've done here is giving you an example. Let me just kind of scroll down below here, in which I say, all right, the logarithmic function log, let's say, base 10 of x, and we actually have another way of describing log base 10. It's actually a very special log. We'll get to that in a second. But let's say I haven't been introduced to that yet, and I have a log base 10 that I want to graph. Well, you can use this relationship introduced here for very basic parent logs. You can get the inverse very easily by coming up with the exponential counterpart to that, in which they have the same base and the argument is actually in the exponent position, and the exponent, the thing the log is equal to is usually the exponent, but those two have to switch in order for you to get the inverse. Hopefully that makes sense and isn't making things more confusing. In any event, just to be clear, it's always the safest thing to go through the inverse calculation steps where you switch the x's and y's and solve. Okay, so, and once we get deeper into the process of converting between exponentials and logarithms, once we have that practice, it'll become a little bit more clear what I mean by that and being able to make the distinction. So anyway, looking at this graph, notice in blue we have the exponential with a base 10. And so the logarithm base 10 would be its inverse. And you'll notice that when you graph these and you have those three main points of 1 over a, 1 and a as being the outputs for your exponential and your inputs being -1, 0, and 1, you switch those and you get the curve of your counterpart logarithm, your inverse logarithm, that is. So just as we know it has to be the case because these two functions are inverses, they are indeed beautiful reflections over the y equals x axis. Okay, so there's a little bit of a visual for you. And they need not necessarily be on opposite sides of the axis. The y equals x line, that is, it's not an axis, it's an orthogonal line. But so they could cross definitely and come back again. It's happened for sure, depending on what kind of, or touch rather. They could definitely touch that y equals x line. This is just one simple example. Okay, and yes, I have this warning here that I want to definitely highlight for you. If you have a more complex logarithm than just the function, then the inverse is going to be more complex than just doing that simple thing that was presented here. I want to present it as a shortcut. If your logarithm doesn't have any extra bits to it, no shifting, no scaling, then you can just go from one of these to the other very simply. But if there is any shifting or scaling, please do not try and just switch your bits out so simply like that. Go through the process outlined in 4.2 where you calculate what the inverse of a function is. Just to warn you, okay? Here I've lifted this little blue box from the book. It's just an overview of the properties of logarithmic functions. So, and again, this is a very standard, not shifted at all, not scaled parent logarithmic function. It has this domain and this range, what we would expect because this is the range and domain respectively of the corresponding inverse exponential. And the x-intercept of the graph is 1. There's no y-intercept. It's like everything that you know to be true about the exponential base a is going to be true about the logarithm base a, just, you know, in reverse. Switch the inputs and the outputs, and there you have it. That's basically the main point. Now, to streamline a couple of very famous logarithms, there are some bases that are used so often that they have their own specific notation, and that'll be the common logarithm, which is outlined here, and then also the natural logarithm. So the common logarithm is this one right here. Here's the natural logarithm. It's basically logarithm base 10. Log base 10 is what you see right here. So notice that there's no base listed for this logarithm. It's just y equals log x. No base, the default is base 10. And you can see it right here in the equivalent equation. That's the exponential version, okay? So furthermore, the base e logarithm, this is a log base e. That constant number, it's called the Euler number, right? And it was a very common base that comes up in a lot of financial and ecological modeling. So it's definitely shows up again in the log realm, and it just, when you see ln, which is the natural log, you know, it's a little bit backwards, I guess, and how you describe it. It's a log with a base of e, basically. So it's like, you would basically, for the log base 10, it's like you don't have that notation, you go for this, and you never say log base e. If you have a log with a base of e, then you don't ever write that, you write natural log instead. Okay, cool. So a little bit of changes in notation. Okay, so now I believe we're ready to fire into some examples, and I have a ton of them for you because I really want you to be able to see very clearly the process of converting either an exponential equation into a logarithm, or, you know, the logarithm into an exponential. So first, we're going to have several examples, and I took these straight out of the textbook. Even numbered problems, so, you know, if you're looking to your textbook for more practice, these ones are not going to be in the back of your book as far as the answers are concerned. So let's go through the process of converting this. So what's my mantra? The base is the base. So off to the side here, I'm going to put the work associated with my conversion style. Okay, so the base of this exponential equation is 4. So that means the log equation version of it will be log base 4. The argument is what the exponential is equal to. What's the exponential equal to? 16. So that's what goes inside of the log function, so to speak. And the log is always equal to the exponent. What's the exponent? It's 2. And that's it. That's all we're being asked to do here for this first bit of practice, is just convert your exponential equation into its logarithmic equivalent, okay? Moving on to the next example. The base is the base. So I've got log base a. I don't know what the value of it is. That's okay. We don't need to know. We're just practicing converting. So the logarithmic equation equivalent will be base a. The argument is what the exponential is equal to. That's 2.1 in this case. And the logarithm itself is equal to the exponent of 3. Cool. Conversion complete. Done. Moving on to the next one. The base is the base. Oh, the base is e this time, so I'm not going to put log base e. Careful, right? You want to put natural log. The argument is equal to the exponential, so the argument will be m this time. The logarithm is always equal to the exponent of 2.2. And there you have it. So hopefully this isn't going too fast and people are feeling comfortable with that. Once you get the mantra down, it goes pretty quickly, I would say. And again, the mantra is the base is the base, the exponential is equal to the argument, and the logarithm is equal to the exponent. Cool. So those were exponential equations that got converted into logarithms. Now let's just start with logarithms and convert them back into exponentials. So remember, the base is the base. So the base log base 3 here means that I'm going to have an exponential. Oops, let's be consistent with that marker here. Here we go. So the base of my exponential will be 3. The log is equal to the exponent, so the exponent should be -2. And the exponential is equal to the argument, which is 1/9. Done. Again, remember, we're just converting. This is not actually anything that you can solve. All the numbers are there. And it makes a true statement there. Indeed, 3 to the -2 power is 1/9, but that's not the point of this. The point is just to practice converting. Okay, let's go ahead and move on to number 22, where we have the base is the base, base b. The log is equal to the exponent. Exponent is 2. The argument is what the exponential is equal to, and that's a 4 this time. All right, one last one in this set. Let's convert. Okay, the base is the base. What's the base here? Well, natural logs are base e, so that means my exponential will be base e. What's the exponent? It's a 4, because that's what the log is equal to. And the argument is the item that I set the exponential equal to. And there we go. Cool. So that was some rapid fire examples of going through the process of converting exponential equations into logarithmic equations, or converting logarithmic equations into exponentials. The 3-part mantra will get you there. That 3-part mantra does a lot for you. But now we have a separate set of examples that we're going to tackle here, in which we are slated with trying to find the exact value of each logarithm without using the calculator. So what I recommend that you do for these, for each one, is you do one particular step to start with, and then use the mantra to convert it into an exponential. And that will illuminate for you, as long as you know rules of exponential expressions, like all of those particular rules, negative exponents and fraction exponents, all that stuff, then you'll be fine. Okay, so again, my first step is to set this equal to x. Sorry, let me try that one more time. Oh, Lord, let me just make a straight line here, equal to x. Okay, and then if this is a logarithmic equation, then I'm going to go ahead and convert it into an exponential. So the base is the base, 8 is the base, that's this little number here. The log is equal to the exponent, and the exponential is equal to the argument, which is also an 8. So 8 to what power equals 8? Well, it's got to be 1, right? So the only way that you'll be able to, get through this is to say, all right, I know that any number with no exponent on it has technically an invisible exponent over 1, and you can slash away the bases at this point and say, okay, well then x equals 1. So relying back on what we know is true from the exponential function stuff that we just went over, that's definitely going to be helpful here. Again, let's start this next one by setting it equal to x and converting it. The base is the base, so that's 1/3. The log is equal to the exponent. Okay, and let's put parentheses around that 1/3 so that we recognize that that entire fraction is indeed the base, and that's going to be equal to the argument, which is 9. Okay, so how do we get through this problem? Well, I noticed that I have values on either side of the equation that could be rewritten base 3, so that's what I'm going to go for here. So base 3. How would I do this? Well, I have a 3 in a denominator space. I can rewrite it with a negative exponent, which would look like this: 3 to the -1 power, but then further raised to the x power. And then 9 can be rewritten as 3 squared. You guys see where I'm going with this? Now I can multiply these exponents together a la power rule, and I'll get 3 to the -x power equals 3 squared. Now I have two exponential expressions on both sides of the equation with the same exact base. Slash away those bases, and that means -x is equal to 2, so therefore x equals -2. Okay, moving on to the next example here. Again, set it equal to x. That's what I recommend you do as your first step for all of these types of problems. And then convert. The base is the base. The log is equal to the exponent. and the exponential is equal to the argument. Okay, now these definitely can both be written base 5. So, oh, 25 rather, excuse me. I almost biffed it there. The radicand here for this cube root is definitely 25, not 5. Okay, so everything has been written correctly. Okay, so I'm ready to write both sides of the equation as base 5. Because I want to get exponential expressions on both sides of this equation with the same base. So I could do that here as long as I can rewrite this. So let's do this in steps. That cube root can be rewritten as a 1/3 power, okay? And I definitely want to think about these things in terms of exponents whenever possible. So if you have any kind of root, rewrite it as the fraction exponent equivalent in order to get through this process, okay? So then 5 to the x power is equal to 25 can be rewritten as 5 squared, but then it's still raised to the 1/3 power. Let's use a little bit of power rule to multiply these two exponents together, and we will get 5 to the x power equals 5 to the 2/3 power, right? Because 2 times 1/3, that's 2/3. We can go ahead and slash away those bases. X equals 2/3. And we're done with that one. Okay, last one in this set. Let's do the first step that we've been doing all along. Set it equal to x and convert. Now, it's a natural log that we're dealing with here, so that's a log base e, excuse me. So that'll be e to the x, right? Because the log is always equal to the exponent, is equal to the argument, which is square root e. Now, anytime you're dealing with a root, go ahead and rewrite it as fraction exponent, and you will find right away that we have the ability to slash away the bases of e, and x equals 1/2 here. And that is that. So once you get this conversion process down with using the mantra, if it's helpful for you, if you have other ways of remembering how to go from one type of function to the other, then that's cool. Like, do you, okay? But this is the way that I do it, and it works for me. So hopefully you get some enjoyment and use out of that. Okay, so for this next example, we have a logarithmic function proper, a log base 5, of x plus 1 over x. Okay, so, you know, pretty complicated logarithmic function here. The only thing we're asked to do here is to find the domain of the function. So I want to remind you guys that the domain of any logarithmic function, basically the argument itself has to be greater than 0 strictly, okay? So I'm going to just circle this argument. Oops, I'm going to actually not use that pen. I'm going to use this and say arguments for logs always must be positive. Okay, so and you can think about the basically that's related to the range of the exponential functions, as long as they no, they always have to be positive. Okay, so what do we need to do here? We basically need to take the argument x plus 1 over x and have it be strictly greater than 0. We need to solve this inequality, but recognize that you have a rational expression inequality here, so that warrants that we do a little number line analysis. You remember this, Jim? Okay, and the first thing that we want to do with our number line analysis, though, is figure out what the critical points are. Okay, critical points are going to be when the numerator equals 0, basically, because it can't equal 0, it's got to be strictly greater than, or when the denominator equals 0. So the numerator equals 0 when x is -1, and the denominator equals 0 when x is, well, 0. So those are going to be our two critical points, -1 and 0, for our number line analysis, and we want to put open dots here to indicate that those points themselves cannot be part of the solution, because neither one of them satisfy this inequality here. So we want to be testing what's going on all the different areas in between and on either side of these critical points. So I'm going to choose inputs of what? -2 here to test, -0.5, and then +1 over here. Just the easiest numbers that I can manage given the bounds on the intervals provided. Okay, so if I put in a -2 here for this ratio, I get a negative number on top and a negative number on bottom, so that means that it ends up being positive, right? And I want this ratio to be positive, greater than 0, in order for it to satisfy this inequality. So this is part of the solution set right here. Now when I plug in a -0.5, I get a positive value on top, but a negative value in the denominator, so that's ultimately negative. So that'll be no, not part of the solution set, the interval between -1 and 0. Testing 1 in here, I get a positive over a positive, so that ratio is ultimately positive and then part of the solution set. So therefore, the solution set here for x is going to be coming up from -infinity, going all the way up to -1, but not including that endpoint, and unifying that with 0 to infinity. So that gives me the interval notation representation of the domain. And that's perfectly fine to give that particular type of notation with your domain. You could word it differently if you wanted to use set builder notation, but I'm going to just leave it this way, mostly because that's the way they are doing it in this textbook section, and that's how they're presenting the final answers in the back of the book. So that's what the author is intending you to do in regard to this example. Okay, great. So let's move on to the next example where I want to get a little bit more visual with it. So you see there's a set of examples here, a set of problems that have graphs of various types of logarithmic functions. They're all base 3, you might notice, but they have various reflections, shifting that's going on here. So we want to make sure that we are keeping fresh this idea of being able to plot functions using transformations, okay? So let's go ahead and go through each of these 8 problems together, the set numbers 65 through 72, being able to identify the logarithmic function given the graph. Okay, so starting with number 65, this looks like your standard logarithmic function, but flipped over the y-axis. That's what I'm seeing here, okay? So which one, A through H, looks like it's flipped over the y-axis? Well, that would be B right here, okay? So B, oh, actually, I'll mark it this way, because it's flipped over the y-axis. Okay, compared to the parent function of just log base 3 of x. That's what I mean here. Okay, number 66 looks like it's shifted 1 unit to the right. So which one of these functions look like that? Well, that would be f, because it's shifted 1 unit to the right from the parent function. Again, 1 unit right. Okay, number 67, well, that one looks like it's flipped over the x and the y-axis. It looks like there was a double flip right there. And as far as the logarithmic functions listed are concerned, D appears to be one that's flipped over the x and the y-axis. Flipped over x and y-axis. Number 68, that one looks like it's flipped over the x-axis and shifted up by 1 unit. Okay, now how do I see the shifting up by 1 unit? Well, it's crossing the x-axis at 3 rather than 1. Okay, so that's how I'm getting the idea by that shift. So which function looks like it does that? Well, that would be function h right here. See, there's the flip right there and shifting up by 1. So h. Flipped over x-axis and shifted up by 1. Sorry, my handwriting is atrocious. All right, moving on to number 69. 69, that one actually looks like the parent function for log base 3. So that's going to be A, and I'm just going to call it the parent, base 3. Cool. For number 70, it appears that we have the parent flipped over the x-axis. All right, so doesn't it look just like this, only, you know, flipped over this horizontal axis? Indeed it does. So flipped over x-axis. And which one appears to be exhibiting that in the function list? That would be C right here, which we see here. There we go, having that -1 factor out in front. For 71, it appears to be shifted down by 1. Again, look at where it's crossing the x-axis. Yeah, so that's how I'm getting that, shifted down by 1. And which one appears to be exhibiting that in the function list? That would be E. Number 71. And lastly, number 72, well, that one looks like it's shifted, but that one's probably the most challenging one to see. It's shifted 1 unit to the right and flipped over the y-axis. So flipped over y-axis and shifted 1 unit to the right. And let me give you a little bit of insight into how I'm picking that this is being exhibited by G. I mean, well, really G is the last one anyway, so it's like you could go by process of elimination on that one. But see here, I want to show you that this can be rewritten as -1 times x minus 1. So that might make it as inside of the argument. So that might make it a little bit easier to see that it's shifting over 1 unit to the right, so that's the x minus 1, and then this is flipping it over the x-axis, is the -1 factor right there. Okay, so hopefully that all makes sense and is feeling good, but if it's not, let's go ahead and definitely talk about it in class. Now, here is the last example in this section in which I want to take this logarithmic function given in number 82, the log, and it's going to be base 10 of a -2x. That's why there's no base explicitly written there. Again, when you see no base and you see the log in there, it's base 10. If there's no base but it's an ln, that's base e, but that's a different one. Okay, so I want us to find the domain and range of f and graph it, and then find the inverse of f, which is going to be the exponential, okay, counterpart, and get its domain and range, and graph them on the same set of axes as f, okay? So let's first start by graphing the exponential. I think that that is the best way to go about this, not having access to a graphing utility. Well, to be clear, I am going to use a graphing utility in order to plot this, but I'll do it in steps so that you can see how you would plot it. Like I'm just using the graphing utility so that my curves are really pretty. That's all. But I'm going to show you how you can get there without, of course, relying on that, which is definitely the purpose of this. So if this is the function in question, in order to come up with the, the inverse, we would, so basically call this a y, but then switch it. So the function inverse in the first step would be x equals log of -2y, right? So the x's and the y's would switch. And then we need to use the 3-part mantra in order to convert it into the exponential counterpart now that we have the inverse, okay? So then that'll be, well, the base is the base. Well, what's the base of this log? It's base 10, right? And the log is equal to the exponent, and then the exponential is equal to the argument. So now we just have one more step to complete in order to get y completely by itself, and that'll give us the actual inverse of this function. So we need to divide both sides by -2, or Another way to represent this would be to multiply it by -1/2, okay? These are equivalent ways to get rid of the coefficient on the y here. And I like keeping this as a separate, what's it called, factor, instead of just dividing by -2 is just looks a little bit funky over here, considering the way that we've been dealing with exponential expressions like the c times a to the x format. I want to maintain that. So that's what this will be right here, okay? Your c value is your y-intercept, right? And then the a value is that the base of the exponential. Okay, great. So let's go ahead and take this and we'll go exponential. And let's give ourselves at least the first three standard inputs of -1, 0, and 1, and then the corresponding outputs will be -1/20th, -1/2, and -5. Okay, so there's the exponential. And then if we want to get the corresponding standard 3 inputs and outputs for the, what do we call it? The logarithm. So the log will have the x's and the y's switched, right? So those standard inputs and outputs will be -1/20, -1/2, -5, and then -1, 0, 1, right? Okay, so let's go ahead and reveal. Okay, so anyway, but before we get too into the graphing, like we're ready to graph, but I do want to address the whole domain and range thing, which is something that they wanted us to talk about. So the domain is going to be, okay, hold on just a second. I'm getting a phone call. I got to take this real quick. Sorry for that interruption. Let's go back to what we were talking about, the domain of the logarithm. So that'll be what I have in blue here. Is going to be, excuse me, -∞ to 0. Okay, it's not any different than the parent, right, for any logarithm ever. And then the range is going to be -∞ to infinity, excuse me. And then we'll switch them for the domain and the range of the exponential. So I'll put the domain and range for the exponential in this maroon color like it did for the XY table. Yeah, and just switch them. So whatever was the domain for the log, it's going to be the range, right, for the exponential. And it'll make the domain all real numbers for the exponential. Okay, so now we are ready to graph this mamma jamma. So here we go. I'm going to do it in stages. I'm going to first I'm going to start by graphing the 3 points. Now, oh, it's so, I don't know, the logarithm, no, that's the exponential, I'm so sorry. So I went a little bit wild with the color coding. I forgot that I did the exponential in blue, so it's a little bit jarring to see that in blue here because I had exponential in purple. I actually did the exponential in blue for the graph and then the logarithm in orange, like I did for the first figure that you saw, the log base 10 or common log, and then the base 10 exponential. Anyway, so here is first the exponential to start because that was the first thing that we calculated. So I'm talking about this right here, okay? So those are the 3 points, and then here is the curve associated with that, okay, in blue. All right, so great. Then I can plot the logarithmic ordered pairs that are in blue in the written form, but they're going to show up as orange there, okay? Right, so -501, -1/2 and 0, and then -1/20th and -1 is right here. Okay, cool. So, and then draw the line connecting those, keeping in intact what you know to be true about the asymptotes. Now, we weren't asked to find the asymptotes here, but if we did, the horizontal asymptote for the exponential would be, so that would be this, excuse me, the orange is the logarithm, the blue is the exponential. I'm like confusing myself here. I should have been a little bit better about color coding these things. In any event, we are ready to do one last step where we show how they are reflections of the y equals x-axis. That's just a little bit of a bonus, this green dashed line. But just to be clear, this is the blue one, if I'm not mistaken, is the exponential, because it's got, what, 1, -5. Yeah, so this is the exponential. I'll just kind of label it. And then the blue one is actually the log. So hopefully that's not too confusing for everybody. Cool. But just so you know, those standard 3 inputs for your exponential or outputs for your log, if that's how you're going to be graphing these things, starting with the exponential first, and then just switching it to get the log. Switching the inputs and outputs, that is, those will give you enough information to give you an idea of the curve, as long as you know how the asymptotes work. So, of course, there's a horizontal asymptote at the x-axis for the exponential, as you can see here, and then there's a vertical asymptote for the y-axis concerning the log, okay? Cool. So we can do more examples like that if you want in class. But now I want to switch gears over to properties of logarithms, which are introduced in one fell swoop here to begin with. I'm going to show you the ways that I see these things that help me remember how to use these properties, okay? So they don't all have names necessarily, but this one is one of the more basic ones, this first little yellow block here, in which we're basically trying to use the 0 exponent rule and the 1 exponent rule for these. So let me just go ahead and kind of give you some notes here. If we were to convert this into its exponent equivalent, it would be a to the 0 power equals 1, right? Which is just to say anything to the 0 power is going to equal a 1. This is the 0 exponent property, but in logarithmic form. And as I write notes for these, I'm going to change the colors for each one so that we don't get confused too much about these rules. So convert this to its exponential equivalent, and you get a to the first power equals a. Earth-shattering, right? This is the exponent, the 1 exponent property. Like any individual factors could be raised to a 1 exponent, if you like. Okay, switch that color up. Let's go purple with it for this one. Okay, so what's cool about this, these two properties here, is that it feels like cancellation in bringing down the exponent. At least that's the way that I see it. So here, I'm just going to rewrite the generic thing that they have here. They have a to the log base a of m equal to m. Well, the way I see it, canceling it right here, is that it's kind of like the base of the exponential and the log of the same base kind of cancel each other out, and the m just kind of comes down to earth, and that's how you get it equal to m. Okay, similarly, have I used this color yet? Hold on just a sec. Yes, I used that blue color, so I'm going to try not to use that one again. Let's see what else is good. I won't keep that red one in play. Let's go green with it. Okay, and then this one, if you have log base a of an exponential with an a base in it, it's kind of like that log base a and the exponential base itself kind of cancel, and the r gets to come down to earth, and that's how it's equal to r. Okay, so if you think about exponentials with log exponents or logarithms with exponentials, and they all have the same base going on, then you can cancel them out, and the exponents just become the value of that logarithm or exponential, whichever you have. Okay, cool. more properties. Here we go. So for these next ones, they have names. They're called a log of a product, log of a quotient, or yeah, and then you have, excuse me, being able to bring down the exponent. We'll get to that one in just a second. Let's go ahead and talk about log of a product, log of a quotient. So basically my mantra with this is, let's see, lighter green I guess we'll do. If it's a product on the inside, it's a sum on the outside. That's the thing that helps me remember this. Product on the inside means sum on the outside, and vice versa. It goes both ways. You can guess how my mantra goes for the next one. Do this dark blue. Quotient on the inside means difference on the outside. Furthermore, what do we have next? Let's do this hot pink next. Okay, and then, yeah, this is an instance in which, oh, what's this next one? So it's basically like the exponent can come down to earth is or come down to earth in front of the log. Let me show you what I mean by that. So you have an exponential expression. These bases don't match, so we're not going to be doing any like canceling and bringing the r down. But one thing you can do, and let's make sure I have a good contrast color, maybe this lighter blue I guess, is you can bring this exponent in as a multiplier in front of your logarithm. Now that'll become very advantageous to us when we want to expand a logarithm into several terms. So that's an exercise that we're definitely going to exhibit here. Okay, so what else? Okay, so interesting. So that'll be, how would we adjust this one? So this one, it's like the e's cancel. So you would put the x back in front and let the e's cancel. Okay, so let me give you a little bit of a short rundown on this one. Let's go orange with it. And say if we have I'm going to go actually with the other side first. E to the x ln of a. So what they're saying with this one, and I'm going to use the same accent color, is this x could come back up to heaven, I guess you could say, or whatever, come back up to the sky and be an exponent on the a, and then what would that look like? Well, that would be e to the ln a to the x, and then you have bases, an exponential and a logarithm with the same base in same as the exponent, and then I actually want that color. Those will cancel and you'll just have this entire thing kind of drop down and give you your a to the x power. Great, so that's how that property works. That one's a little bit clunkier to work with, but you can get through it as long as you remember the previous properties feed into these later ones for sure. Okay, so I'm going to have to rework with some colors here, nothing too crazy. Let's go back to this light blue color, or teal color rather. So then this is basically just saying that if you have an equation, a logarithmic equation, in which you have just a single log on both sides and they're the same base, it's like you get to cancel them out and the remaining arguments get to be set equal to each other. Okay? Lastly, we have a change of base formula, which is definitely going to be advantageous for us if we need to estimate, like round to some decimal place value of a particular logarithm. Like let's say we had some kind of application going on with some logarithms, and we'll get deep into that stuff. So if you're asking now, oh, where do logarithms and exponential functions factor in as far as like real world problems and applications, we're going to have a couple of sections dedicated to that for Thursday's lecture, for the next lecture after this one, day, I guess 14, if I should just keep it generic. Okay, so anyway, this last one, though, is going to help us in that endeavor if we ever need to really have this particular value of a logarithm of a weird base. You can always change the base like this, and my mantra associated with this is big on top, little on bottom. Allow me to demonstrate. So you have, let's say, and I'm going to keep it generic here, log base a of m. Okay, and let's say you want to plug this into a calculator. So actually you're probably going to be relying more on common logs or natural logs in order to make this conversion happen, but you can technically use change of base to turn it into any log base that you want to. Okay, but in any event, let's go ahead and just for the sake of argument do natural log. Okay, that's probably my favorite one. Is let's say you want to change it to the natural log. So you're going to set it up so that you make a ratio of natural logs or whatever log base that you want, and big on top means, and let me change the color here, big, oh, whoops, I want this color, right? That's this one. The argument is the big number or letter or whatever it is that goes in the numerator space, and then little on the bottom is going to be the base, the old base rather, okay? All right, and that'll get you where you want to go. And you can type that into your calculator because every scientific calculator has a natural log and a common log button, okay? And we'll definitely do a problem just like that before we wrap up for the day, okay? Now, here is just a slew of examples to get you warmed up to these properties. And so here we go. Here's the first one. We are going to recognize that we have an expression with a natural log, so that's a log base e, and it has an exponential of the same base. So that means we get to slash away those two bits and bring this down. So that's going to give us a final answer of the square root of 2. Okay, now moving on to this next one. We are going to recognize that a sum on the outside, right, it represents a product on the inside of a single log base 6. So I'm going to use that, I think it was a product rule for logarithms is what it might have been generically called. Some such name was given, and put 9 times 4, these two arguments, together inside of 1 logarithm base 6. And then what is 9 times 4? You can certainly simplify this further. That'll be 36. And can we rewrite 36 as something base 6? So we can use that the same property that we used in number 16. Well, sure we can. Log base 6 of 6 squared, right? Log base 6 and a base of 6 are able to cancel out, and we're just left with 2. So then 2 is your final answer for this one. All right, moving right along. I see a product of 2 logarithms with different bases. Furthermore, and I'm just going to highlight this as the meaning behind why I'm going to do the next thing that I'm going to do. I just have a wealth of experience with problems like these. When you see 2 logarithms multiplied together and the argument of one is the base of the other one, this is asking you to use a change of base formula, basically, okay? And you can do the change of base for common log, natural log, any other log that you want, but you're going to notice that when you do this, I'm going to choose the common log just for no particular reason, okay? And so change of base for this first factor would be log of 8 over log of 3. Remember, big on top, little on bottom, okay? And I'm going to multiply that by, that's this multiplication here, change of base again for the common log, big on top, so that's log of 9 over log of 8. All right. And see how the log base 10 or common log of 8 is diagonally across the way in this product of ratios? Now, how would you have looked at this original problem and known to do that? Well, you probably wouldn't. So I'm just wanted to make sure I did this problem so that you could see how nicely that works out if you use a change of base in order to cross those out. So then, what do we have next? Well, we're going to do a log of 9 over log of 3. Okay. And so then you can go back and use the change of base again, but in the other direction, and say, okay, well, this should be log base 3 of 9, right? Big was on top is the big number, and the bottom is the little number, or the base, if you're using change of base backwards. Again, how would you know to move forward in that way? From experience, and I'm just trying to give you that experience now through this demonstration. Now we have the log of base 3, and we have a number in the argument that can be rewritten base 3. So go ahead and do that, and then recognize that you have an exponential of the same base as the log in the argument. You can cancel out the log and the base, and you're just left with 2. So again, our answer is 2 there. A little anticlimactic because the previous problem's answer was 2. But there you have it. Okay, now this one gets to be quite challenging. This is the last problem in this set of problems in the homework. So I wanted to show you a way to deal with this, because we're going to have a log involved here that's base e squared. Do you guys see that? We have e to the log base e squared of 9 power. This entire thing right here, just to be clear, is the exponent. So let's keep that in mind, okay? Now, how must we deal with this? Yikes. So it's going to be a multi-step process, and I'm actually going to use 2 separate variables to get through this. I know that sounds wild, but just bear with me here, okay? And actually, I'm going to change the color just to mix it up here. Okay, but that entire thing is the exponent. So if we set this equal to x and convert it into a logarithmic counterpart, some things are going to fall into place for us, okay? So remember, the exponential is equal to the argument. So this is, and it's a base e, right? So this will be the natural log, or do we want to call it log base e? I know natural log is the way to go about it technically, but let's just call it log base e for the time being. I know that sounds a little bit counterintuitive, but just stick with me here. So log base e of, right, the it'll be x, is equal to log the entire exponent, right, which is log base e squared of 9. Okay, now let's go ahead and say, because we want to split these into 2 different cases, right, but they're both equal to the same thing, so I think it would behoove us to introduce another variable here. So let's call this case 1, where it's log base e of x equals y. And then here's case 2, log base e squared of 9 also equals y. And let's figure out what we can do in regard to converting them, okay? So, and also let's recognize that this can be rewritten as some base squared, okay? So there's several things that are happening all at once, which might not be super intuitive. So let's call this 3 squared. So if we go through the motions of taking this and writing it as an exponential, it'll be e to the y power equals x, right? This is e to the y power equals x. Let's keep that in mind. Okay, but that's supposed to be equivalent to what's going on here, which is e squared to the y power equals 3 squared. Okay. So then we can take these two exponents, and it's kind of like we're taking the square root of both sides. In fact, if we took the square root of both sides, we could get rid of these two exponents, boom, boom. And then we would have e to the y equaling, equaling 3. Well, e to the y over here on this one side, right, equaled x, and then here I'm saying e to the y equals 3. Since they must be equal to each other, we can, through the transitive property, say that x therefore has to equal 3, which is the value of the original exponential with the logarithm inside. Wow, I know, pretty wild. But that's how we're going to get that final answer. That was definitely the most challenging one in that set. So if you were looking at that and you're like, what? Don't worry, we can talk about it more in class, and I can give you more examples of that style. Okay, but for now, let's go ahead and just move forward and write the expression down below as the sum or difference of logarithms. So definitely we're going to use that some of these properties with the sums on the outside, meaning products on the inside, and the difference equivalent, and then also bringing the exponents down as factors. In fact, that's going to be our first move here. So I'm going to pick a new color. Let's take that magenta one. And I'm going to start by taking this exponent and making it a factor out in front. So that'll give me 2/3 times the natural log. Oh, actually, I don't need a bracket here. Let's get rid of that bracket for the moment. 2/3 times the natural log, because I have this bracket here, of x minus 4 quantity squared over x squared minus 1. Okay. Then I want to use the fact that we have a quotient here in order to split these two numerator and denominator factors into separate natural logarithms, keeping in mind that 2/3 is a factor out in front, and I'll distribute through when I'm at the end of this expansion process. That'll be like one of the last steps that I perform. So that'll give me the natural log of x minus 4 squared minus the natural log of x squared minus 1. Okay? So then, in the next step, I'm going to recognize that two things are happening here. I'm going to get another color going. Recognize that I have a factor of 2 that I should put in front of this natural log. And furthermore, this x squared minus 1 bit can be factored into x plus 1 times x minus 1, right? So we have a product inside of the second natural logarithm, which can be expanded out as a sum on the outside. So let's go ahead and from here continue, and we will get 2/3 times quantity 2 natural log of x minus 4 minus, and we got to expand it out a little bit, the natural log of x plus 1 plus the natural log of x minus 1. At this point, we have some distribution to do in order to get it in the final form that we want here. So let's be very mindful about this. So this 2/3 has to multiply all the way through. This negative sign has got to be put in front of these 2 natural logs inside of this innermost bracket, and there we'll have it. Okay, so actually I just want to write the final answer here. 2/3 times this 2 that's already waiting will be giving us 4/3 natural log of x minus 4 minus, don't forget about that 2/3, it's got to go here and here as well, 2/3 natural log of x plus 1 minus 2/3 of the natural log of x minus 1. Okay, and there we have it. So I know what some of you might be thinking, don't we have work to do inside of these arguments? No, we don't, because it's only products and quotients inside of logarithms that become sums and differences outside of logarithms. It's not, there's not a similar rule for sums or differences inside. So we want to be careful with that and making sure that you're not mixing things up there. Okay, great. Now I think we only have a few more to go. Let's see, we're going to condense this one up, and then we're going to do a change of base to approximate. So not much more left. I know this video has already gotten quite long here. So here we want to notice that we have all the same base logarithms, log 3, and we have a sum and a difference, and we have a multiplier in front of this particular term right here. So how do we want to deal with that? Well, I would deal with this 21 multiplier out first and call it an exponent of 21 on the cube root of x. So, and we're going to deal with that as the cube root as a fraction exponent. Just bear with me here. First I'll just write it like this, and we'll deal with the 21 afterwards, and we'll just rewrite everything else for the time being. Okay, now let's deal with this. Now this is actually an exponent of 1/3 times an exponent of 27, so that will in the next step give me an exponent of 7, right, on the x. Is everyone following me there? This is x to the 1/3 power, then further raised to the 21st power. 1/3 times 21 gives me 7. So hopefully everybody can follow that. And then again, I'll just rewrite everything else as is for the time being. In the next step, I'll deal with the sums and the differences one at a time. I recommend that you don't do too much at once for this. Okay, let's first just deal with the sum and make it a product inside of a single logarithm. Actually, we could all do it all at the same time. I'm okay with that. Yeah, let's do a product here. And then it has to be divided by this, and then divide this. Okay, yeah, we could do it all in one go if we're feeling comfortable. So that's log base 3 of, we have x to the 7th times 9x squared all over 9. That's supposed to be a raised dot, and that's supposed to be an x. So sloppy. Okay, do we have any simplifying to do here? Oh, yes, we do. Cancel out those 9s and multiply those x's together, and you will get log base 3 of x to the 9th power. And that's it. We have expressed this in a single logarithm, and we have simplified it as much as we possibly can. All right, so we're done there. Cool. Last problem in this set, or in this lecture, that is we're going to use the change of base formula in a calculator. Scientific will do. More powerful calculators can also handle this, but a scientific calculator works perfectly fine to approximate its value to 3 decimal places. Okay, keeping that in mind. All right, so what I'm going to do is change this from a log base 5 to a common log. Okay, so changing to common log. It's going to go, we'll want log over log, no base, because that's the common log doesn't have base explicitly shown, although we know it's 10. And then we're going to put a big number on top, small number on the bottom, right? And it's just as easy as that. So do some button pushing, and depending on how you do it, if you can write this all at once, cool. If you're going to do it in pieces, these are going to be approximately, the log base 10 of 18 is about 1.25527250. 0.051, blah, 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 blah. Okay, and then the log base 10 of 5 is about 0.698970004, blah, 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 blah. Okay, now, depending on what kind of calculator you have, you might need to take this in pieces and then do the division. And just make sure that you take it out to an exorbitant number of significant figures for each individual one, so you don't have any round off error. Regardless, you should get something around going to 3 decimal places, that is 1.796. And if you got something really close but not right, then that means that you're experiencing some round off error and you just need to take more significant figures of the pieces that you're using before you make the division happen. Okay, that is it for today. Let's go ahead and have a rousing logarithmic discussion in class. I can't wait. See you then.